Hello, Brief Calculus students. Section 12.3. Second derivative is actually talking about how fast a derivative changes. And we like this to use the terms of velocity and acceleration. So I left this in terms of preview. So there are animations here on this figure, 1 and 2. So preview. Okay, we've got some different things going on. So if I click on number 1, you can see that I asked it to take 2 seconds to come in, and number 2 was just 1/4 of a second. So let me see if I slow that down. What does it look like now? Okay, it's a little bit easier to see. I'll take it down one notch. Okay, we can change velocity, and we call it acceleration. That's when we step on the gas. We've accelerated. We've changed how fast we're changing. So, calculator time. Okay, I took this equation from the last one, the homework, and I modified a little bit. I changed it to a 4th power instead of a 3rd. So here's the first derivative, and then here's the second derivative. You see how it keeps coming down? The 0.12x squared becomes 0.24x becomes 0.24. And the 0.9's gone, the 0.0. Yeah, it's a derivative. And right here, I've turned off the second and third equations, so when I graph it, okay, only the first equation shows up. So a 4th degree equation can look like a W or an M. And we know the first derivative will tell us about slope. And right here, where it's got the maximum and minimum, you remember that. Let me change the window. Okay, so I come down along the equal sign and hit enter. And then the window, I'm going to make a little bit smaller. Let's see, we're going between -10 and 10. So what if we change that to -2 to 2. Graph. Okay, remember the blue is the first, is just the function. So it's a lot clearer to see the minimum maximum here. And then you know as the first derivative comes down, and that little ball just is a way of signaling, hey, I'm here. Okay, so it told us the slope was positive, and when we go between positive and negative, we have a max. Then we come negative to positive, right there at the 0, we have a relative min. Then we go positive slope down to negative slope, and right there, we have another relative max. So there we go. The question is, why in the world do you need the second derivative? Well, let me come here to the y equals. I'll just show you how, enter, turn it off, and then enter, graph. So this is graphing that cube function, and we just treat, the derivative is going to work the same way. We had a positive or a negative slope, and then a relative min, and a positive slope, relative max, and then we're back down to we just go back down. We have a negative slope. So the derivative of this function right here says it was a negative slope, came up to positive slope. So right here we had a relative minimum, because we went from negative slope to positive slope, so that's a min. Alright, we went from positive slope. No, we went from a negative slope up to a positive slope. Okay, so yeah, that was a minimum. Sorry, I have to do the hand figures. You'll see me in a test. Okay, and this one went from positive slope up to relative max. So the derivative function of this is showing we had a positive slope that went to 0 to a negative slope. So it went positive, 0, negative. So that is definitely a max. So when you go negative flat, positive, chicken wings. Okay, yeah, that's a negative. So what happens? Let me turn on the original function, but turn off the first derivative graph. So here's our m. It's a marvelous function, darling. And a second derivative. Okay, obviously they're related because, you know, they're both symmetric. Looks like one of those DS controllers, right? Or PS4? I don't know, I just started playing it. Anyway, what is going on here? We had something that was negative. We went to positive. We went back to negative. We had zeros. So what was going on? Let me grab this piece of paper right here. The answer is we're not measuring slope anymore. We're measuring the way the slope is changing. In this case, the slope is concave down. There's a little rhyme, I guess, that goes, concave down is like a frown, concave up is like a cup. This one right here is concave down because as it goes down, you know, it goes down faster and faster and faster. So it's going up right here. Yeah, it is increasing, but it's increasing at a slower and slower and slower rate. That means concave down. Right here, it was increasing at a slower and slower rate. Then it started decreasing and getting decreasing. And then once that decreasing started going faster, then it started becoming concave up because it actually started coming back up. So this second derivative of the function is measuring concave down to a 0 to concave up because it's positive, back to concave down. And these points right here in the middle where it equals 0 are what we call point of inflection, or if we are doing the right sort of business functions, it will actually be a point of diminishing returns. So, what does your second derivative function tell you? It says, you know from that your first derivative, that you found some zeros. Are they minimums or maximums? Okay, let me go back to turn on the first derivative function. Okay, so we have a 0 here, and we have a 0 here, and we have a 0 here. Are those minimums or maximums? Well, at this point, we were concave down. So, concave down was like a frown. So, that's a maximum, isn't it? That point was a relative maximum. Even though I don't see the first function, I can see that this 0 right here, using the second derivative, saying it's concave down, that's a maximum. And this is where some people get really confused. They're saying, wait, your second derivative is negative. How can this be a maximum? Well, you almost have to draw a picture. Think of like going downhill. Alright? You have a maximum there. And then where this 0 is right here, it was positive, so that's concave up, like a cup. So that 0 is going to sit there and say, oh, it's a minimum. And then right here we have another 0. Okay, I'm looking, and it is concave down. So, I mean, I seriously use my hands for this section. Concave down says that 0 is a maximum. So that is what your second derivative tells you. That's what the second derivative test is. So I am going to pause the video, rearrange the function a little bit, and Let's see what we can tell. Well, it took a while to set up, but here we have a first derivative and a second derivative. And you can usually tell the two apart because the more derivatives you go, first to second to third to fourth to fifth, the simpler the equation gets. So this blue one's a little bit more complicated, so it's the first derivative, it's the second one. And you can check by saying, look, this is a negative slope down to here. It hits kind of a plateau and it starts going up. And this right here has it's negative, hit 0, it's positive, hit 0, right again where we have a plateau. And then they both, we're going negative here. Alright, so given first derivative and second derivative, where are the minimums and maximums? Okay, true question. First derivative says minimum or maximum is going to be right about here, about 2. If I was doing it, I'd say it's got a positive slope, and then it goes to 0, and then it goes negative. So I think it's a maximum, but let me check with the second derivative. Okay, second derivative says right here it's concave down. So the second derivative is less than 0. Concave down says, yes, it is a maximum. It's sitting on top of a hill, a peak. Okay, I do have the original function. I actually used chapter 14 methods I put in the blue line first and then the yellow line or red line and said, okay, what's the original function? Well, that's chapter 13 and chapter 14. What is the original function? It's there, and we'll see it. Okay, so here it says we've got another peak or valley, a minimum maximum right here between 2 and 3. If I was just drawing a line, it was a negative slope, it went flat, went positive, sounds like a minimum to me, but I check and it says second derivative is positive. Well, second derivative positive is concave up, which means like a, cup. Oh, okay, so yes, it is a minimum. And then again, we have one more point. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's close to 10. And I went from positive to flat to negative. Positive to flat to negative sounds like a maximum. Let me check. Concave down, the second derivative is less than 0. Concave down won't hold water. It's like a frown. Yes, that does look like a maximum. Okay, let me turn on the function. Okay, here's the original function. Okay, what were we predicting at the zeros? This was a maximum, a relative maximum, and it was concave down there. Concave down, second derivative is less than 0. This one over here was a relative minimum, and concave up is like a cup. Yay, it's nice and happy. It will hold water. It is definitely a relative minimum. And then here again, where the slope went from positive to flat to negative, positive to flat to negative, it was concave down again. And yes, it is like a maximum, relative maximum. Sorry about that. Okay. Second derivative can be confusing. You're thinking, it's negative here, it's negative at this point. Okay, concave down, that's what it means. And so yes, it is a relative maximum, even where it's negative. And where the second derivative is positive, trying to hold this in front of the screen, it's going to hold water. It's going to be a relative minimum. Don't let it confuse you. So good luck on the homework.